In Chapter 5, our primary concern is going to be work and energy, and we need to provide basic definitions to make sure they make good sense. So work is going to be a dot product. It's going to be force dot displacement. So it's a force vector, and we're going to dot product that with a displacement. Let's talk about what we mean by this initially. So I've got a file cabinet here. So if I apply a force and I pull that maybe 2 meters versus a force and pull it 15 meters, it'll take more energy or work to pull at 15 meters versus the 2 meters. So conceptually, work is how much force I apply in something multiplied by how the distance is in terms of how far I actually travel with that. But what does a dot product mean? Well, work is going to be force times distance cosine of theta. So what that means is the force that's parallel to the motion is what's going to cause it to move in that direction. So if I have, for instance, this file cabinet here, and let's apply a force to that. So I'm going to put a force on that. I will make it off in this direction here. Okay, and let's give that force, let's say a 60-degree angle. Okay, and let's say I'm applying 100 newtons on that. So let's record that 100 newtons right there. Okay, and what about the distance I go? Let's do a dashed line here. And let's say I go 10 meters. Okay, so we learned in Chapter 4 that this is a force applied at an angle. So we will have a force applied y. That force applied y does not make it move in the x direction. Only the force applied x allows it to move in that direction. So if we do force times distance cosine theta, essentially what we're getting is force applied x multiplied by how far we go. So it's a very easy equation. So work is 100. We're going to multiply that by the distance of 10, and then multiply that by the cosine of 60. Then we end up with 500. And what would the units be for this? Well, force is measured in newtons, and distance or displacement is measured in meters. Now guys, this is a scalar quantity when we're done. When we do a dot product, we end up with a scalar quantity, meaning that there's no angle associated with this, no direction with this. Another unit for Newton meter is also joules. Okay, and we just give it the letter J, named after a very famous person, of course. Okay, so joules would be the unit of work. It's also a unit of energy. Work and energy, okay, are synonymous values. Now, the next several slides, we're just going to look at different kinds of work or different kinds of energy. The next one is kinetic energy. Kinetic energy is the energy of motion. You might have heard the formula for kinetic energy before. Kinetic energy is 1/2 the mass of an object multiplied by velocity squared. Okay, and let's say we have a toy helicopter here, 5 kilograms, and this thing's moving at 20 meters per second. So how would I get kinetic energy? So kinetic energy is going to be 1/2 the mass, which is 5, okay, times 20 squared, and that's going to equal 1,000, and that's joules, okay, or Newton meters. Either one you can say would work for. So kinetic energy is a pretty easy calculation to do. And again, it stands for the energy of motion. Now, there are some potential energies. One is gravitational potential energy. You can think of this as the work of gravity. And right now, we're going to just make it positive. We'll worry about positive and negatives later. Gravitational potential energy, GPE, is then going to be force gravity multiplied by the distance we go. And if we're going up and down, we're going to say that's height. So if I have an origin located here, and I move the ball, a football, up 10.5 meters, what's the gravitational potential energy? So we can remind ourselves that force gravity is mg, and how high we go is h. So think of it as the work of gravity. It's the force of gravity multiplied by the distance it goes. If you remember what we've already defined work as force times distance. Now, of course, gravity is always going to be in the same direction as we are pulling, either away from it or with it. So the cosine of 0 applies, so I'm not going to put cosine of 0 there. So gravitational potential energy is mass times gravity, which is force of gravity, times height. So solving for this, pretty easy to do also. Okay, I'm just going to take the mass of the ball, 1.5 times 9.8. That gives me the force of gravity. How far did we go? 10.5 meters. So I just multiply all of those together, and this is going to be 154 Newton meters, or again, joules. Either one, those answers are synonymous. So again, energy of units of joules or Newton meters for work, those are all the same. Now this is a potential energy. Why? Because if I take the ball and I move it up 10.5 meters, it's stored in gravity. If I let it go, the ball is going to fall back downwards. We're going to see later in this chapter that that's a conservation of energy. And gravitational potential energy comes from a conservative force, which is gravity. Okay, the next type, elastic potential energy. This is the energy stored in a spring. Elastic potential energy equals 1/2 kx squared. Hope you remember from our force of a spring equals kx. Okay, k is equal to the spring constant. X is how far the spring is either compressed or stretched. To get elastic potential energy, or EPE, we set it equal to 1/2 kx squared. Okay, this will be derived for us in class later. So let's say I've got a skier who wants to get an initial boost for a spring. Okay, and the spring constant for this, K, is equal to 1,000 Newton over meter. And let's say we compress that spring. Well, let's give it a distance of, I don't know, maybe 0.5 meters. So let's do that. So we push the spring in 1/2 meter, and then we're going to let it go, and it'll release, and then it'll cause the skier to go this way. So again, this is a stored energy. Why? Because we compress the spring, store energy in the spring, then we release it, and we'll get kinetic energy out of it. So what's our equation then? Well, elastic potential energy is equal to 1/2 the K constant. Again, that's unique to each spring. And multiply that by 0.5 squared. And again, that's how much the spring is either compressed or how much it's actually stretched. Okay, either one, the way you want to look at that. Okay, and our energy comes out to be 125 joules. Or I could call that Newton meters. Either one would be fine. So those are our work and energy units, and those are all conserved. In other words, we can kind of convert things back and forth, kinetic energy to potential, back and forth. Now we have a non-conservative one, of course, thermal energy. You can think of this as equaling the work of friction. Now thermal energy has a general equation then. It's going to be the force of friction multiplied by how far we go times distance we go. And one more time, cosine theta. Almost always theta is going to be 0 again, so it's the cosine of 0, which equals 1. Okay, so what if I'm driving a car and I've got a constant force, let's say going against it, of 200 newtons. Okay, and then I'm going to drive the car, let's say a distance of 15 meters. So how much energy has been lost due to thermal energy of friction? Well, again, what the force of friction is 200. How long or what distance did that go through? So thermal energy is going to equal 200. And we're going to multiply that by 15. And that, of course, is going to equal 3,000 joules. Now, again, you're going to see soon that this is going to be a negative value because it's taking away energy from kinetic energy. So those are our 5 kinds of energies. How do we handle that in terms of our work kinetic energy theorem? Well, let's take a look. Well, first of all, we have work that are conservative forces. So the general concept is work is going to go into kinetic energy. But what about these kinds of work? Well, what about work, and then we're going to plus a negative potential energies, any one of those potential energies, okay, and that is going to equal kinetic energy. So how do we really mean this? Okay, this means work plus any kind of negative change in potential energy, that has to equal the change in kinetic energy of the system. Okay, so if I apply work, but some of that work goes into stored energy, that's not going to go into kinetic energy at all. So let's say I'm moving an object upwards. So I might be giving potential energy to the system, but we're not going to see that as kinetic energy. Now, if I'm pushing an object downwards, then my change in potential energy will be negative, but a negative means that that becomes a positive. Therefore, the object's going to go faster and faster and faster. So in that case, since change in potential energy is negative, that will go into kinetic energy. How does this equation change when we've got non-conservative forces, which means work of friction? So this is going to be the work done plus negative work of friction. Remember, that's going to be like our thermal energy. And again, plus negative change in potential energy. And this is going to equal the change in kinetic energy here. So in work, friction will never be positive. It always takes away energy from kinetic energy. So the work plus take away whatever friction, and then plus essentially or minus potential energy change, because sometimes potential energy change will be negative, making this a positive, meaning we're going to see a rise in kinetic energy. And sometimes potential energy, if I'm moving an object upwards, for instance, that'll actually be a positive change. Therefore, a negative of a positive means you're not going to see that in kinetic energy. We'll see plenty of examples that help make that clearer. Okay, so what really is our work kinetic energy theorem? So really, what we can say then is work net goes into the change in kinetic energy. So whatever work is left over, once you take away friction forces and consider any kind of change in potential energy, that's going to go into our change in kinetic energy. What about mechanical energy? Well, mechanical energy really is equal to the sum of kinetic energy plus any kind of potential energy. Okay, and there you have it. So we had in chapter 4, like force net equals mass times acceleration. In this case, we have whatever work net is equals the change in kinetic energy for the system. And that's an introduction to energy. More to come on all of that.